Hi everyone, I'm Casey Luminario and today I'll be discussing to you nuclear structure. Let me give you a brief introduction of my topic. This is Anthony Henry Becquerel and he's the one who discovered radioactivity in uranium compounds. This discovery prompted scientists to investigate the details of radioactivity and ultimately the structure of nucleus. Pioneering work by Ernest Rutherford showed that the radiation emitted by radioactive substances is of three types, which are the alpha, beta, and gamma. In 1911, Ernest Rutherford, Hans Geiger, and Ernest Marsden performed the alpha particle scattering experiments, which is described in section 42.2. These experiments established that the nucleus of an atom can be modeled as a point mass and point charge, and that most of the atomic mass is contained in the nucleus. Subsequent studies reveal that presence of new type of force, the short-range nuclear force, which is predominant at particle separation distance less than approximately 10 raised to the negative 40 meters and is zero from large distances. As we go on, what is nucleus? So a nucleus is represented by the symbol AZX, where X is any chemical element. A denotes the total number of nucleons, and Z denotes the total number of protons. The total number of neutrons is in a nucleus is the neutron number n, where n is equal to A minus Z. What are isotopes? Well, isotopes are nuclei having the same Z value but different A and N values. The natural abundance of isotopes can differ substantially. Now let's proceed to charge and mass. The proton carries a single positive charge E equal in magnitude to the negative E on the electron, where E is equal to 1.6 times 10 raised to negative 19 coulomb. And the atomic mass unit U is defined in such a way that the mass of one atom of the isotope 12C is exactly 12U, where 1U is equal to 1.660,539 times 10 raised to negative 27 kilograms. In order to obtain the rest energy equivalent, we have this equation where ER is equal to mc squared, where m denotes mass and c denotes charge. Let's solve this example. Example 44.1, the atomic mass unit. In this example, we must prove that 1U is equal to 1.66 times 10 to the negative 7 20 kilograms. In order to solve this, first we must conceptualize. From the definition of the mole given in section 19.5, we know that exactly 12 grams, or 1 mole of 12C, contains Avogadro's number of atoms. And then we categorize. We evaluate the atomic mass unit that was introduced in this section, so we categorize this example as a substitution problem. To start with, let's solve for m, or our mass. We have this given mass here, which is in grams, but we have to derive this to kilograms. 12 grams is equal to 0.012 grams, and we divide it by the Avogadro's constant, which is 6.02 times 10 to the 23 atoms. And this equates us with 1.99 times 10 to the negative 26 kilograms. Now, in order for us to prove that 1U is equal to 1.66 times 10 to the negative 27 kilograms, we must divide our mass by our atomic mass unit, which is denoted by U, and our U is 12. Our mass here is 1.99 times 10 to the negative 26 kilograms. I will divide it by our U, which is 12, and this equates us with 1.66 times 10 to the negative 27 kilograms. Nuclear binding energy. The total mass of a nucleus is less than the sum of the masses of its individual nucleons. Therefore, the rest energy of the bound system or the nucleus is less than the combined rest energy of the separated nucleons. This difference in energy is called the binding energy of the nucleus and can be interpreted as the energy that must be added to a nucleus to break it apart into its components. Conservation of energy and the Einstein mass energy equivalence relationship shows that the binding energy EB of any nucleus of mass Ma is EB, or the binding energy, multiplied to the mega electron volt, or the MeV, and is equal to Z, which are represented by the electrons, mH, which is the atomic mass of the neutral hydrogen atom, added to the total number of the mass of the neutron, and the masses are all in atomic mass units, minus the summation of the atomic mass of an atom of the isotope, and multiplied to our rest energy, which was previously solved. 931.494 mega electron volt divided by its atomic mass unit. Nuclear models. Liquid drop model is when the nucleons interact strongly with one another and undergo frequent collisions as they jiggle around within the nucleus. Four major effects influence the binding energy of the nucleus in the liquid drop model. Number one is the volume effect. The contribution of the binding energy of the entire nucleus is C1A, where C1 is an adjustable constant that can be determined by fitting the prediction of the model to experimental results. Number two, the surface effect. Because of the number of surface nucleons is proportional to the surface area, 4 pi r squared, of the nucleus, which is modeled as a sphere, and because r squared multiplied by a raised to 2/3 in equation 44.1, the surface term can be expressed as negative C2 multiplied by a raised to 2/3, where C2 is the second adjustable constant. Number three, the Coulomb repulsion effect. The reduction in binding energy that results from the Coulomb effect is negative C3Z multiplied by Z minus 1 divided by A raised to 1/3, where C3 is yet another adjustable constant. The symmetry effect is the fourth factor. The value of N for stable nuclei is naturally larger than Z. This effect can be described by a binding energy term of the form negative C4 multiplied to N minus Z squared divided by A, where C4 is another adjustable constant. When we add up these contributions, this gives us the following expression for the total binding energy, where EB is equal to C1A minus C2A raised to 2/3 minus C3 multiplied by Z times Z minus 1 all over A and 1/3 minus C4 and N minus Z squared all over A. These are only used for a semi-empirical binding energy formula. Let's solve this example here. Example 44.3, applying the semi-empirical binding energy formula. The nucleus 64 zinc has a tabulated binding energy of 559.09 mega electron volt. Use the semi-empirical binding energy formula to generate a theoretical estimate of the binding energy for this nucleus. Now, in order to solve this, we must first conceptualize. Imagine bringing the separate protons and neutrons together to form a 64 zinc nucleus. The rest energy of the nucleus is smaller than the rest energy of the individual particles. The difference in the rest energy is the binding energy. Then we categorize. From the text of the problem, we know how to apply the liquid drop model. This example is a substitution problem. Going to our problem, We have C1, which is equal to 15.7 mega electron volt, C2, which is equal to 17.8 mega electron volt, C3, which is equal to 0.71 mega electron volt, and C4, which is equal to 23.6 mega electron volt. We have our A here, which is equal to 64. In order to solve C1A, we must multiply 15.7 MeV, which is the C1, and A, which is 64, and this gives us 1005 mega electron volt. In order to solve C2A raised to 2 thirds, we must substitute our value for C2, which is 17.8 MeV, multiplied by our A, which is 64, raised to its exponent 2 thirds, and this gives us 285 mega electron volt. In order to solve C3, Z times Z minus 1 all over A raised to 1 thirds, we must substitute our values for C3, which is 0.71 MeV, multiplied to 30, which are C, and 30 minus 1 is 29, all over 64 of 1 thirds, and this gives us 154 MeV. And in order to solve C4 n minus Z squared all over A, we must substitute our value for C4, which is 23.6 MeV, and our n is 34, minus 30, which is our Z squared all over our A, which is 64, and this gives us 5490 MeV. And using the liquid drop model, we just have to add and combine all of the equations we have, or all of the parameters, into the EB, which is equal to C1A, which is the 1005 MeV minus 285 MeV minus 154 MeV minus 5.90 MeV, and this gives us 560 MeV. And the equation is solved. The shell model. The shell model of the nucleus, also called the independent particle model. In this model, each nucleon is assumed to exist in a shell, similar to an atomic shell for an electron. There is a factor influencing the characteristics observed on nuclear ground state, like the nuclear pin orbit effects. The spin-orbit interaction between the spin of an electron and its orbital motion in an atom gives rise to the sodium doublet and is magnetic in origin. The spin-orbit effect of nucleons in a nucleus is due to the nuclear force. Now let's proceed to radioactivity. Radioactivity is the process of spontaneous emission of radiation by uranium. Additional experiments, including Rutherford's famous work on alpha particle scattering, suggested that radioactivity is the result of the decay, or the disintegration or unstable nuclei. Three types of radioactive decay occur in radioactive substances, like alpha decay, in which the emitted particles are forged in nuclei; beta B decay, in which the emitted particles are either electrons or positrons; and gamma G decay, in which the emitted particles are high energy photons. What are positrons? Positrons are particles like the electron in all respects except that the positron has a charge of positive E. The positron is the antiparticle of the electron. So if N is the number of undecayed radioactive nuclei present at some instant, the rate of change of N with time is dN over dt is equal to negative lambda N, where lambda is also called the decay constant and is the probability of decay per nucleus per second. The negative sign indicates that dN over dt is negative, that is, N decreases in time, where it can be written in the form dN over N is equal to negative lambda dt, which upon integration gives us N is equal to N sub O e raised to lambda t, negative lambda t. The decay rate R, which is the number of decays per second, can be obtained by combining equations in 44.5 and 44.6, where R is equal to the absolute value of dn over dt and can be written as lambda n is equal to lambda n sub o multiplied by e raised to negative lambda t, which will be r sub o multiplied to e raised to negative lambda t, where r sub o is equal to lambda n sub o is the decay rate at time is equal to 0. The decay rate r of a sample is often referred to its activity. Note that both n and r decrease exponentially with time. Another parameter useful in characterizing nuclear decay in the half-time is T 1/2. The half-life of radioactivity substance. Shit the fuck up. The half-life of a radioactive substance is the time interval during which half of a given number of radioactive nuclei decay. To find an expression for the half-life, we first set n is equal to n sub o divided by 2, and t is equal to t 1/2 in equation 44.6 to give n sub o divided by 2 is equal to n sub o e raised to negative lambda t 1/2. Canceling the n sub o factors and then taking the reciprocal of both sides, we obtain e raised to lambda t 1/2 is equal to 2. Taking the natural logarithm of both sides gives t 1/2 is equal to the natural log of 2 over lambda, which will be equal to 0.693 all over lambda, or the day. We have an example 44.4. How many nuclei are left? In this example, it says that the isotope carbon 14, where A is 14 and Z is 6 carbon, is radioactive and has a half-life of 5,730 years. If you start with a sample of 1,000 carbon 14 nuclei, how many nuclei will be undecayed in 25 years? So in order to solve this, we must first again conceptualize. The time interval of 25 years is much longer than the half-life, so only a small fraction of the originally undecayed nuclei will remain. Categorize. The text of the problem allows us to categorize this example as a radioactive decay problem. And then we analyze. We have to divide the time interval by the half-life to determine the number of half-lives. This gives us n. We have to divide the half-life to determine number of half-lives, which will be 25,000 years divided by 5,730 years, and this will give us 4.363. And that will be our n. And then we have to determine how many undecayed nuclei are left after 4.363 half-lives. In order to do this, we must use our equation capital N is equal to n sub o multiplied to 1/2 raised to n. And substitute all the parameters, we'll have 1,000 times 1/2 raised to 4.363, and this will give us 49. To finalize the result, as we have mentioned, radioactive decay is a probabilistic process and accurate statistical predictions are possible only with a very large number of atoms. The original sample in this example contains only 1,000 nuclei, which is certainly not a very large number. Therefore, if we counted the number of undecayed nuclei remaining after 25 years, it might not be exactly 49. The decay process. We have here alpha decay. So it's a nucleus emitting an alpha particle 4,2He or helium loses 2 protons and 2 neutrons. Therefore, the atomic number Z decreases by 2. The mass number A decreases by 4 and the neutron number decreases by 2. The decay can be written as AZX to A minus 4 and Z minus 2Y plus 4 to helium, where X is called the parent nucleus and Y is the daughter nucleus. As a general rule in any decay expression, such as this one, the sum of the mass numbers A must be the same on both sides of the decay, and the sum of the atomic numbers Z must be the same on both sides of the decay. As examples used, 238U and 226Ra are both alpha emitters and decay according to the schemes. Beta decay is when a radioactive nucleus undergoes beta decay. The daughter nucleus contains the same number of nucleons as the parent nucleus, but the atomic number is changed by 1, which means that the number of protons changes. Whereas mentioned in section 44.4, E negative designates an electron and E positive designates a positron, with Bella particle being the general term referring to either. Beta decay is not described completely by these expressions. We shall give reasons for this statement shortly. Carbon dating. The ratio of 14C to 12C in the carbon dioxide molecules of our atmosphere has a constant value of approximately 1.3 times 10 to the negative 12. The carbon atoms in all living organisms have the same 14C divided by 12C ratio because the organisms continuously exchange carbon dioxide with their surroundings. When an organism dies, however, it no longer absorbs 14C from the atmosphere, and so the 14C divided by 12C ratio decreases as the 14C decays with half-life of 5,730 years. It is therefore possible to measure the age of a material by measuring its 14C cavity. Gamma decay. A nucleus that undergoes radioactive decay is left in an excited energy state. The nucleus can then undergo a second day to a lower energy state, perhaps to the ground state, by emitting a higher energy photon, where AZX is to AZX plus Y, where X indicates a nucleus in an excited state. The typical half-life of an excited nuclear state is 10 to the negative 10 s. Photons emitted in such a excitation process are called gamma rays. Such photons have very high energy, or 1 megaelectronvolt to 1 GeV, relative to the energy of visible light, approximately 1 eV. Natural radioactivity. Radioactive nuclei are generally classified into two groups. Number one, the unstable nuclei found in nature, which give rise to natural radioactivity. And number two, unstable nuclei, produced in the laboratory through nuclear reactions which exhibit artificial radioactivity. Nuclear reaction. Collisions which change the identity of the target nuclei are called nuclear reactions. With today's advanced technology in particle accelerators and particle detectors, it is possible to achieve particle energies of at least 1000 GeV to 1 TeV. These high-energy particles are used to create new particles whose properties are helping to solve the mysteries of the nucleus. Consider a reaction in which a target nucleus X is bombarded by a particle A, resulting in a daughter nucleus Y and an outgoing particle B, where A plus X is to Y plus B. Sometimes this reaction is written in the more compact form where X A B Y. The Q value for this reaction is 17.3 megaelectronvolt. A reaction such as this one, for which Q is positive, is called exothermic. A reaction for which Q is negative is called endothermic. To satisfy conservation of momentum, an endothermic reaction does not occur unless the bombarding particle has a kinetic energy greater than Q. The minimum energy necessary for such a reaction to occur is called threshold energy. Nuclear magnetic resonance and magnetic resonance imaging. Nuclei also have spin because their component particles, neutrons and protons, Each have spin as well as orbital angular momentum within the nucleus. The magnitude of the nuclear angular momentum is where I is called the nuclear spin quantum number and may be an integer or half integer depending on how the individual proton and neutron spins combine. Nuclear spin has an associated nuclear magnetic moment similar to that of the electron. The spin magnetic moment of a nucleus is measured in terms of the nuclear magneton mu n, a unit moment defined as q is equal to ma plus mx minus my minus mb multiplied to c squared. And that's it for my presentation. I hope you learned a lot from me. Again, this is Casey Luminario. Goodbye.